Hi everyone, it's Mr. Zarzik, and in the screencast, I'm going to talk about a fairly common scenario that pops up in AP Physics. That's when you have a force that's related to velocity. And that's what this F is equal to negative CV thing is here up on in the title. Okay, what it says is that as velocity gets larger, the force gets larger, but there's a little bit more to it as well. There's that C in there, which is just a constant, and then the negative sign is an indication that the force that we'd be talking about would be some kind of resistive force. So in other words, as an object moves faster, it experiences a greater resistive force to that motion. The force and the velocity are in opposite directions. This is the kind of thing that shows up when you try to model, say, like falling with air resistance. Okay, so as you fall and as you speed up, as you gain velocity, the amount of air resistance you're going to experience increases. And what we find is that as an object falls, if its surface area doesn't alter, it follows a relationship that's roughly linear. Okay, that's really what this says. Force is equal to the minus times some constant times the velocity. This kind of a scenario shows up actually in a lot of different cases, so we're going to look at one of those here today. And the consequences of that, of how we do the analysis, is interesting. It can be pretty complicated, can be pretty simple, and be pretty interesting too. Okay, so let's get right into it. All right, so I said this is fairly common, so this is a type of problem where this sort of relationship between force and velocity shows up. It says a bullet is fired into a block of wood at a velocity of v naught. Okay, that's a little v naught in there. Sorry, the text got a little messed up there. The retarding force is equal to negative CV. So the resistive force. So the bullet flies through this block of wood. The faster the bullet moves, the bigger the resistance, the force. The slower the bullet moves, the less the force. So you can think is that when the bullet would enter the block of wood, it would experience a large amount of force, and then that would slow it down. As it slows down, the amount of push that it would feel, the resistance from that wood would get smaller. That would follow this linear relationship. Okay, so it says how far does the bullet penetrate into the wood? I'm going to show you three different methods. Now, all of them are dependent upon the mass of the bullet. Okay, so for the purpose of this problem, we're just gonna make the assumption. We're going to assume that the mass of the bullet, we're just going to call it M. Okay, so some mass. All right, so I'm going to show you three different methods. Okay, we're going to start with the most complicated, and we're going to work into one that's simpler. All right, so here we go. So we'll call this one method one. All right, so we've got a force function. So what we're going to do is we start with what we know about force, which is just Newton's second law. So that's F equals ma. All right, where m is the mass and a is the acceleration. The acceleration, by definition, is the change in velocity with respect to time. So if I write that as a differential, F equals m dv dt. Okay, we're going to need that. We're going to need that calculus to solve this. All right, the force function is that minus CV, so I'm going to replace force with that minus CV. We get this m dv dt. All right. As it's set up, this is set up as a differential, so we're going to wind up integrating, and the way we're going to do that is we're going to move that dt over, so multiply both sides by dt, and we get this negative CV dt is equal to m dv, which is mass times the change in velocity, which you might recognize as that's the change in momentum, which is why in the title we had that momentum that was associated with this F is equal to minus CV. All right, so on the left-hand side, we've got the change in time. Okay, so we're going to integrate over there with respect to time. But on the right-hand side, we've got the change in velocity and that little dv on the right-hand side. So the v is on the left over here. So we're going to take and remove the v over by dividing it out to both sides, which leaves me with c dt on the left and m divided by v dv on the right. Okay, now we're ready to do our integration. So we're going to integrate both sides. Okay, so if you think about this, the bullet is going to enter the block, and that's where we're going to start the clock. So we're going to start at time 0, all right? And we're going to integrate up until some time. We're just going to call that t. Okay, so we're going to get a generalized expression. All right, likewise, in the given information, it says the bullet's fired into a block of wood at a velocity of v naught. So that's our initial condition for velocity. All right, now the bullet will eventually stop. We will reach a final velocity of 0, all right? But much like I've done on the left side, I'm going to write this just as a general v because we're going to get a general expression. All right, the reason I'm doing this is twofold. One, it has to do with the mathematical function that's going to pop here in a second when I do my integration. And then more importantly, we're looking for how far the bullet penetrates. So that's a position function, and our setup does not yet have position. So just follow along with me, you'll see what I mean here. All right, so left-hand side, the integral of negative c dt would just be c times t, because there's no variable in there, that's just the dt. So we're going to integrate from 0 to t on the left. Okay, m is in the numerator, v is in the denominator. The m is just a constant, and really I'm integrating 1 over v. All right, you might remember, or if not, look on the AP equation sheet. The integral of 1 over x is the natural log of x, or in this case, the natural log of v, where I'm going to evaluate from v naught over v. Okay, and if you are really good with your math and your functions, you know that the natural log of 0 is an undefined number, okay, which is why we want to avoid that 0 in there, number one. And then number two, like I said, we're trying to find a position function, and we're not at position yet. All right, we're getting there. All right, so left-hand side, let's evaluate. So we've got negative c t minus negative c of 0. Okay, right-hand side, we get mass. I'm just keep the mass on the outside. So we've got natural log of v minus natural log of v naught. All right, so that was c times 0 is 0, so that just goes away. So we're left with negative ct on the left. Okay, and this is another little math trick. If I have ln of v minus ln of v naught, you can also write that expression as ln of v over v naught. Those two things, that ln of v minus ln of v naught and ln of v over v naught, those two are equivalent. All right, stay with me. We're still going here. So I'm going to move that m over to the left-hand side. So I get ct over m equals natural log of v over v naught. Okay, and we want to get that v out of there. You'll see why here in just a second. And so here's our trick. Okay, if I go ln of v over v naught, okay, if I take and I apply the e function, so e raised to the ln of v over v naught, and what I need to do on the one side, I have to do on the other. Okay, well then e to the ln of any function just gets you the function that's inside. In other words, e to the ln of v over v naught is just v over v naught. All right, so pretty useful little trick. It pops up a lot in physics. So we get e to the negative ct over m. All right, I'm going to take that v naught, I'm going to move that over to the left-hand side. So v naught e to the negative ct over m is equal to v. Okay, and you might be saying, where are we going with this? Well, what is velocity? It's the change in position with respect to the change in time. So if I just rewrite velocity on the right there, remember that v, that's just the general term for velocity. That's the variable term. It's the change in position with respect to the change in time, okay? And now I'm getting a little closer to what I actually care about, which is how far, what's the displacement of the bullet as it moves through the wood. Here, let me show you. V naught e to the negative ct over m. I'm going to move that dt over. Okay, and what I have here is I have another integral. I'm going to integrate on the left-hand side with respect to time. And I'm going to integrate on the right-hand side with respect to position. All right, we start the clock at time is equal to 0. All right, now when does the clock end? Now this part's kind of subtle. All right, we've got v naught, which is just some initial, it's how fast the bullet's going to begin with. And then we've got this function e to the negative ct over m, where c is a constant, m is a constant, t is the variable. So really what we're looking at is e to the negative x. All right, so then the question is at what time does this become 0? This is a graph of e to the negative x. See, there it is, e to the negative x. Okay, well, what we're looking at is a decaying exponential. So it is not until time infinity does the bullet actually come to rest, at least according to our function. All right, and so we have to associate our integration with it. We have to integrate all the way out until time infinity. And that will tell us if we start with the edge of the block of the wood, the bullet penetrates to some displacement s. I know that's a lot, but stay with me, okay? We're almost there, all right? And again, this is the tough method. I'm going to show you the easier approach here in just a minute, okay? So anyways, let's just take care of the right-hand side first. That one's a little bit easier. So 0 to infinity, v naught e to the negative ct over m, dt is just equal to s from 0 to s. All right, now let's take care of that left-hand side. It's a little tougher, all right? Let's see, so v naught is a constant. Okay, the integral of e to the x is just e to the x. It's another one of those funky identities. All right, so let's see. So we've got e to the negative ct over m. All right, but we have to worry about the exponent. In other words, like the integral of e to the 2x would be e to the 2x, but there'd also be the integral or the derivative of 2x to worry about if we went the other directions. Like if we took the derivative of e to the 2x, we'd have e to the 2x times 2. Okay, so kind of like what we do with say, like if we integrate x squared to be x to the third over 3, we have to account for that extra coefficient piece based upon what the exponent is raised to. So let's see, so the derivative of ct over m with respect to t would be negative c over m. That means we need negative m over c as a coefficient. Okay, we have to evaluate from 0 to infinity. All right, on the right, we've got s from 0 to s. That'd be s minus 0, so just s. Okay, and then here's my evaluation. All right, so I'm going to bring that s to the left-hand side to make this a little bit easier to see. Okay, and let's see, so that'd be negative m times v naught over c. All right, so that constant just times e to the negative ct over m, evaluated from 0 to infinity. Okay, so just taking my time here because this is kind of messy the first time you see it. All right, so that would be negative m v naught over c. All right, so let's see. So we've got e to the negative c times infinity, which is still just, well, now it's negative infinity divided by m, which is still just negative infinity. E to the negative infinity, okay, minus, let's see, so it'd be e minus c times 0. 0 over m is still just 0, so e to the 0. Okay, and here it's finally going to start to clean up a little bit. Okay, as e to the negative x approaches infinity, that's when that e function approaches 0. So this right here goes to 0, and e to the 0 is just 1. So we've got negative 1 on the inside of our brackets. So we got 0 minus negative 1, which is negative 1. So you got negative, negative. These are positives. All right, and after all of that, we're left with this relation mv naught over c. Okay, so it actually simplifies down pretty nicely there. So the displacement of the bullet as it enters in the wood is equal to its mass times its initial velocity divided by this c. Wow, that was a lot. Okay, I wonder if we could find something simpler. And the answer is we do have something simpler. There's two other methods. Okay, so method number 2, all right, which is going to get us the same answer. Here we go. Method 2. All right. So again, we start with what we know. So we got this force function of minus CV, but the definition of force, okay, is mass times acceleration, like Newton's second law. Okay, and we still have acceleration as the change in velocity with respect to the change in time. Okay. And the given force function is still this minus CV. So minus CV is equal to m dv dt. All right. So we've still got calculus that has to be done. All right, but we're going to take a little shortcut because, well, this force function it depends upon velocity. And what is velocity? It's the change in position with respect to the change in time. So I'm going to write that velocity as ds dt is equal to m dv dt. All right, now notice here's the shortcut. Okay, both of these in our setup have dt, and both those dt's are in the same spot. They're in the denominator. Now it's a differential, but we still can follow the same rules of algebra. It appears on both sides, which means that we can cancel each by. Okay, and this simplifies down and becomes much easier to work with now. So minus c ds is equal to m dv. Mass times the change in velocity. Hey, that's impulse. Okay, that's why we have that title, momentum up in the title, because this seems to keep popping up. All right, so I am going to integrate. All right, on the left-hand side, the bullet pierces the wood at position 0. Okay, and it's just displaced to some position s, so I'm going to integrate from 0 to s. On the right-hand side, the initial velocity is given as this v naught. All right, and here the final velocity is going to shrink to 0. All right, much simpler now. So what do we get? We get negative c times s, evaluated from 0 to s, is equal to mass times velocity evaluated over from that initial velocity until it stops. All right, and so let's see. So we wind up with negative cs minus c times 0 is equal to mass times 0, minus mass times initial velocity. All right, so goodbye. All that goes away. Look at this. Negative cs is equal to negative mass times initial velocity. Negatives cancel. Oh, so much easier. Cs is equal to mass times initial velocity, and so the displacement s is equal to the mass times the initial velocity over this constant. Okay, and still requires calculus. Okay, it's still a little bit tricky in terms of the setup, but we get the same answer as we did before. All right, pretty cool. There's actually a third method that we can do with this. Okay, and it's worth looking at because this third method allows us to solve the problem without any calculus. It's like, oh, this is an AP problem. You can only do it with calculus. You can only do it with calculus. Not true. Okay. We can actually solve this problem. We just came out of our work energy unit. So starting with the definition of work, which is the change in energy, the bullet enters the block of wood. When it does so, the wood is going to slow the bullet down, so it's going to experience a change in kinetic energy. All right, the block of wood is going to do work on the bullet to change its kinetic energy. So delta is final minus initial. All right. If the bullet is going to come to rest as it is displaced through the block of wood, okay, that final kinetic energy goes to 0. Okay, and so on the right-hand side, I'm left with minus KE initial. Okay, and work, just the simple basic definition of work, okay, is force times displacement. Now, that's just a specialized case of work, okay, so a less specialized case would be Ft cos theta. An even less specialized case would be F dot D or F dot S, okay? But again, this is the original version of what we learned about work. So this is the simplest case mathematically. All right, now the caveat is that if we use force times distance, we'll really hear this is just average force. Okay, so we could use this equation back in honors physics before we had any calculus. But when we used it, what we were really talking about was an average force. Very often we'd use it with like when the force remains constant, so we didn't have to worry about that. Well, here the force does not remain constant. Here force follows this minus CV, which is a linear relationship between force and velocity. Because of that fact, okay, I'm going to put this over on the side. All right, average force is really just the initial force plus the final force divided by 2. It's really just the arithmetic mean, okay, between the two. And again, we can get away with this because the force is linear proportional to the velocity. The thing is slowing down as it moves through the block of the wood, so we can use this here, okay, which is actually really, really cool. All right, initially the force is that minus CV, where the V is that initial velocity that we're given. And if at the end of this problem, the bullet stops, well, in minus CV, if V is equal to 0, then the force is equal to 0 as well. Okay, so the average force is just then minus CV naught over 2. Okay, so let me go ahead and plug that in back over here on the left. Okay, so I get this minus CV naught over 2. There's my force times my distance is equal to the negative of the initial kinetic energy. And, well, initial kinetic energy, the general form, is just 1/2 times mass times v squared, where it starts with this thing that we call the v naught for the initial velocity. Okay. Notice here that the negatives appear on both sides, so they just cancel out. Okay, in both cases, you've got a 2 down in the denominator, so that cancels out. And we also have V naught on both sides. So here it's squared and here it's just V naught. Okay, so most of this simplifies down. So I got C times D is equal to M times V naught. Okay, and so the amount that the bullet is displaced through the wood is equal to M V naught over C. Lo and behold, we get the same answer that we got from our two previous methods. Okay, so two methods with calculus, one disgusting, one less disgusting. One method without calculus, just algebra and the recognition of average force. All right, very cool. So I hope you enjoyed watching this. Definitely take a look back through this because there's a lot of steps. And this is Mr. Zarzik saying we'll see you next time.